Okay, good morning, everyone. It's nice to see everyone. Welcome to the spring Compton lectures. For those of you I haven't met, I'm Ed Lucher. I'm the director of the Enrico Fermi Institute that sponsors these lectures. So I'm particularly excited about the spring's lecture series because the topic is the research area that I work in. Our speaker is Thomas Wester. He was an undergraduate here at the University of Chicago, took classes in this room, I remember. He did his graduate work at Boston University, and he'll talk to you about, I think, the beautiful picture, well, on the poster, was from the experiment that he did his dissertation work on. Then he came to Chicago as a McCormick postdoctoral fellow in the Fermi Institute, and I think you'll hear a great story from him. So, Thomas.
Okay. Thanks so much to everybody for coming. Hopefully, Mary, the audio is good. Okay, great. So let's get started. So yeah, thanks to Ed. As Ed mentioned, I was an undergraduate here. So about 10 years ago, I was sitting where you're sitting, and Ed was standing up here. So this is kind of weird, but we'll see how it goes. So yeah, this series, this Compton lecture is about neutrinos, and specifically neutrino detectors, and how we use neutrino detector technology to understand about the universe and these really interesting particles. So you might have heard recently, there was some news articles posted about ultra-high energy neutrino detected with a telescope under the sea. So a really big flashy headline. And if you just look at this, maybe you have some questions. I don't know, what does ultra-high energy mean? What is a neutrino? Sounds kind of scary, actually. Should we be worried? I'm not sure. And then also a telescope under the sea. Like, what's that? What does that mean? Why would we put a telescope under the sea? What good does that do us? So there's also one other part of this, which is that we have no idea where it came from. And that is a little unsettling because we've been detecting neutrinos for a long time, as I'll talk about today. So the fact that there's one that appeared and we don't know where it came from is a big mystery. So I'll be unpacking this and other stories like this from neutrino physics throughout these lecture series. I just want to make a quick plug that this article was written by Katrina Miller, who is a graduate of the University of Chicago in the neutrino group. So look out for her reporting in the New York Times. She's been doing great science reporting. Okay, so anyway, this telescope under the sea, this is real. So here's a video of the telescope being constructed. This is a ship in the Mediterranean Sea deploying strings of sensors. So the ship takes these light sensors that are wound up into a big ball. The strings are submerged. They go down to the bottom of the sea where they're anchored. And this video is showing that whole process. So the ball here is on this anchor thing, and then this robot arm comes and it pulls this tether, which is going to release all the sensors, which will then float up, as you'll see. So this is kind of an amazing feat of engineering to put this whole thing together. And you can repeat this whole process for multiple strings to build a detector that is actually functioning as a telescope and literally under the sea. So this is just a video. Here's one of the light sensors that's being deployed, and then here's the roll being taken out. So this is what this actually looks like. So this is the telescope and what was published in Nature just a couple months ago, or in February. Here are the strings shown here that were deployed. This is the Eiffel Tower for scale, so you get a sense of how big this thing is. And what these sensors are picking up on are charged particles that deposit light as they travel through this array. And the pattern of light on these strings tells you something about the particle's energy and the direction. And so this is the telescope. This is how a telescope works. You look at light or a particle or something, and you try to point back to where it came from. So we can do this with this neutrino, and we point back to the region of the sky where it came from, and there's nothing there. So we haven't identified the source of this neutrino yet, but we're working on it. So anyway, I'll talk more about this detector throughout this series and a lot of other ones. So there are lots of really cool stories from neutrino physics, and neutrino physics also takes you all over the world. So this is an example of an experiment I worked on. This is in Japan, Kamioka, a huge detector, 20 Olympic swimming pools filled with water, covered in really intricate light sensors, a giant electromagnet coming through a very small town in Germany, slightly inconveniencing the local population for an afternoon as it made its way across the countryside. I'll tell you about that one too. And then finally, extreme conditions. So IceCube, the detector here, built in the South Pole in Antarctica. So what's the reason why we do all of this? So how do we get here? So the basic idea here is that all of these experiments, what they have in common is that they're here to study a fundamental particle called the neutrino. So the neutrino, not quite 100 years old, 95 years old, but it was first theorized to solve a very basic question in physics. And once we solved that question, we realized that the neutrino had a lot of mysteries of its own. So we kept going. We kept building bigger detectors and doing more complex experiments to understand really what this particle is all about. You might also ask how I got here. So as Ed mentioned, I was an undergraduate at the University of Chicago. I started doing some research on detectors back here. This is a picture of our little tiny detector over at the basement of the ERC building just next door. And it was filled with a little bit of xenon, and operating that was a great experience for me. I also did some commuting to Fermi Lab nearby out in the suburbs, where I worked on the microboon experiment for a couple summers. Then I moved out east to Boston. I did my graduate work at Boston University, and my commute changed slightly to work on the Super K experiment. I took a bunch of trips over to Japan to build this detector and see it operate. Finally, I came back, thanks to Ed's invitation to become a postdoc here. My commute looked very similar to what it did as an undergrad, but now I've added Argonne National Lab. So we're building a new experiment at Fermi Lab that came online earlier this year. And then also I've been doing some work at Argonne on their computing clusters. So that's a little bit about my background. And then for this lecture series, I hope that you'll all take away just 3 things. So neutrinos, why these tiny particles are worth the trouble. That's kind of the big picture point of this. And then also, I hope you learn all about the different techniques that we use in neutrino experiments, neutrino detectors, and how we can use those to learn more about fundamental properties of our universe. And then finally, what's next? So the neutrino physics is really just getting started. There's a lot of questions we have and a lot of things we have learned, but a lot more to learn. Okay, so then just a little logistics. This is the schedule. So today's lecture is going to be all about discovering the neutrino. And then I have mapped out just a couple other topics that I want to talk about. It's kind of preliminary, so we'll see how it goes. And this might change slightly, but this is the overall plan. Okay, and so with that, start with lecture number 1, discovering the neutrino. Okay, so I'm going to start with physics as it looked 100 years ago. So put yourself in 1925. What did we know? What did we not know? So first of all, we knew radioactivity. These are some famous names that you might have heard: Henry Becquerel, James Chadwick, the Curies. These people were studying radioactive decays. And so we had that as a nice experimental probe. At the same time, we had another group of physicists working on quantum mechanics and building the math that we use to describe the universe. And then somewhere in between, we had some experimentalists. So J.J. Thomson and Ernest Rutherford were taking the radioactive decays that was kind of considered a chemistry field and bombarding atoms and then trying to map those onto different predictions of quantum mechanics. But all of these groups of physicists were concerned with one thing, which is what is the structure of the atom? The atom was kind of our proving ground for understanding if our mathematical description of the universe worked. So we had the data coming from these folks over here, and then predicted by quantum mechanics as a test. So radioactivity was kind of our best tool for this. So you have an atom over here, and you wait some time, and then it decays into a different atom, plus some radiation. And this is really fundamentally all that's going on. And what you can do is you can start to categorize and study the radiation. So Rutherford did this. He made a table of the different types of radiation that he observed. He called them alpha, beta, and gamma, and separated them based on how far the different types of radiation would penetrate into different materials. So alpha particles were notoriously easily blocked. You could put a piece of paper in front of an alpha decay source, and the alpha wouldn't go through. Betas would go a little bit further, and then photons would go even further still. So then there are two questions that you could ask about decays. You can ask what's the energy of the thing that comes out, and then how often does it happen? It turns out that answering the question about energy is not too hard. We can do it in a couple of lines of math. So I won't do too much math during these lectures, but this one I think is worth showing. So as physicists, we're going to try to simplify our problem down to its core elements and see exactly how to put the pieces together. So you can think of an idealized decay as a nucleus A, and then it transforms into another nucleus B, and then some piece of radiation C. And we're going to use A, B, and C just as stand-ins to do some calculations. Oh, we'll need one other piece, which is of 1920s physics. This is Einstein giving us his little E equals mc squared, with a little correction there for things that move. This is the p squared plus c squared part over here. Okay, so the math looks like this. You start out with conservation of energy. You have EA, which is the energy of the A, and it equals the energy of the two things that come out, EB plus EC. Now, I know that Einstein is going to give us something that has a square root in it, so it might be wise to anticipate that and kind of make our equation a little bit nicer. So I'm going to rearrange some things here. In this line here, I'm just moving the EC to the other side, and then I'm going to square both things so that I don't have square roots at the end. But so far, so good. Just taking this starting from conservation of energy. Next, I'm going to plug in Einstein's equation. So that looks like E squared is m squared plus p squared. I've dropped the c's. They're going to cancel out in the end, so we won't need them. But that means that EA over here transforms into MA, so the mass of the A particle. And then you can make that substitution over here. For the C and the B, you actually have this momentum term, this term that describes the motion of the particles. So you get one of those for the EC squared and the EB squared. Thankfully, by momentum conservation, these two things are actually the same. So before and after the decay takes place, these have to be equivalent, so they end up dropping out. And what you find is that the energy of the C, so of our radiation, just depends on these masses. So the mass of the thing you started with minus the mass squared of the thing it decayed to, plus its own mass gets a little contribution, and then there's another term in the denominator here. Okay, so this is just kind of a jumble of constants at the moment, but what really is fundamentally going on here is that this EC over here is just a constant. So what you learn from this is that every time you have a radioactive decay, you can describe the energy of the radiation just as a fixed number. So something happens repeatably every single time. So what I wrote here is radiation from nuclear decays should always have the same fixed energies up to the resolution of our detector. What that might look like is if you put a radioactive source and then measure the radiation, the energy of the radiation, you would get a repeatable number of counts in your detector at the same energy each time. Now it can happen sometimes that radioactive elements can decay to multiple things, so you might see different spikes here, so decaying to different states, but ultimately it's just a collection of different single-valued energies. So you can actually look at some data for this. This is an alpha decay measured pretty recently. Americium-241 is the element, and it basically looks like we expect. So there's one big spike here at 59.54 keV, kilo electron volts is the unit here. And then there are a bunch of other spikes down here. So this is great. Our theory is working really nicely. We can use just very simple relativistic mechanics to figure out how this radiation should behave. One slight topic, which is not too off topic, but this is the same element that you find in smoke detectors, actually. So before maybe about 2005 or so, smoke detectors were based on this technology where an alpha particle would be, there was a little alpha emitting source in the smoke detector, and that alpha would impinge on a little capacitor, but then if there's smoke in the way, then the smoke blocks the alpha particles, and it sets off the smoke alarm. So we've since made better smoke detectors, but for a long time, this is how they worked, just based on alpha decay. So you can do this same process, but for other things. So I mentioned the three types of radiation, alpha, beta, and gamma. Let's look at beta decay. Okay, so something went wrong here. This is the beta decay spectrum, and this was known about in 1927. There are no spikes. It's just a big, broad distribution. And this was the work of 3 physicists and plus others, but Chadwick, Lisa Meitner, and then Charles Drummond Ellis. They worked together to kind of figure out if this was really a continuous spectrum and not just maybe lots of discrete states. But eventually, they were all convinced that something was very different about beta decays compared to alpha decays and gamma decays, which had these single lines. So this was a big problem, and nobody knew how to explain this. So all of the quantum mechanics that we had applied, all of Einstein's relativity, it didn't really match this picture. So what you do in physics when you are faced with a experimental result that doesn't match your theory is you go back and you check your assumptions. So let's think about what we assumed when we first calculated the energy of the alpha decay spectrum. So one thing that was the contribution by Lisa Meitner was testing whether or not the beta maybe encountered some other process as it exited the nucleus or exited the atom. So maybe the electron was emitted, but then it scattered or something. So actually, Meitner did observe this, but found that it only accounted for some of the beta decays. There was truly a continuous spectrum underneath, but it could happen. But observing it was a critical step of this. Niels Bohr, a famous physicist, was actually ready to throw energy conservation out the window. So remember when we started our calculation, we assumed that energy was conserved. So if you remove that assumption, maybe you don't get these fixed energy peaks. So this was Bohr's idea. But somebody else, Wolfgang Pauli, famous for the Pauli exclusion principle, had another idea, which is that maybe more than one particle is emitted. Now, this is an intriguing idea, and Pauli wrote a letter about his idea to a conference that was going on in Germany. So the letter is over here, but I've taken out some excerpts from this. So it starts off very nicely. Dear radioactive ladies and gentlemen, I have hit upon a desperate remedy. Okay, so what does that mean? And the desperate remedy means that he's tried all other options, but really wants to save conservation of energy. So the desperate remedy is that there could exist in the nuclei electrically neutral particles that I wish to call neutrons. The continuous beta spectrum would then make sense. In addition to an electron, so you're not only emitting an electron, the neutron is emitted such that the sum of the energies between the electron and the neutron is constant. But so far I do not dare to publish anything about this idea because, so why was Pauli reluctant to publish anything about the idea? Because he hadn't done the math. He had no evidence to back this up. It was just pure superstition or hypothesizing. Just, hey, maybe there's this particle out there, and if there is, then maybe it would explain the beta decay spectrum, but I don't know how it fits into quantum mechanics. I have no evidence that this particle exists. And then at the end, just a quick note about how he's currently indisposed going to a ball, instead of being at this conference talking about this with all of his colleagues. Okay, fine. So hopefully he can catch up later. So here's Pauli's idea in a nutshell. Alpha decays look like this. One emitted particle gets all the energy, and so the total energy of the decay is shown by this line here. But beta decay is special, so instead of having just one particle that comes out, you have two, and that means you can split the energy between the electron and the neutrino, called the neutron at the time. And you would have a continuum of this because the split here would be random, and we'll see how that plays out in a little bit. But in this way, you see the electron, but it comes out at different energies, and you miss this guy in gray. So you don't see that. And that's why every time you measure a beta decay, you don't see the full energy of the decay. Instead, you just see part of it. Okay, so it's a nice idea, but it took some time before it was actually fully fleshed out. So Enrico Fermi, who was a professor at the University of Chicago during the last years of his life, was actually the one who saved us and saved Pauli's idea. So Fermi took Pauli's idea and then made it into something that was consistent with quantum mechanics. So what Fermi did was take the model of Pauli, so where nucleus decays into a beta plus a neutrino, and figured out how to make it continuous. So calculating the probabilities from quantum mechanics of each individual energy split, and then adding them all up and making showing that that led to a continuous spectrum of the energies of the beta particles. So one other thing Fermi did was noted that there's no force known at the time that would describe this process. So Fermi had to invent a new force for this. And then it was also at this point where Pauli's neutrino got renamed to the neutrino, or Pauli's neutron got renamed to the neutrino, which in Italian means little neutral one. So big contributions from Fermi. It was then up to two physicists, Hans Bethe and Rudolf Peierls, who took Fermi's theory and tried to calculate something meaningful out of it. So by itself, Fermi's theory just is still just kind of a hypothesis. It hasn't proven any real thing exists in the universe. It just shows that it could be explained, or it is consistent with the math that we know about. But these two physicists, they took the normal beta decay reaction here that Fermi's theory described, where you have a neutron and becoming a proton and then emitting an electron, also known as the beta, and then a neutrino, and they flipped it around. So they took this process, they shuffled things around, and they predicted that, so if you emit a neutrino, then maybe you can have a neutrino interact with a proton and emit an electron that you could then observe. So this was the idea. Now you have a solid prediction that somebody could test. If you had a neutrino, you could watch to see if, when it interacted with a proton, does it actually produce this E plus that I'm showing here and this neutron. But they were actually pretty pessimistic about this whole thing. So they wrote this paper that tried to calculate the probability of this process happening. And what they came up with was a number 10 to the minus 44 centimeters squared. So that's a very small number, as it turns out. To put that in perspective, what they interpreted this as is the neutrino in this process would travel 10 to the 16 kilometers in solid matter before interacting, before making this observable signal. And they concluded based on that that it would be absolutely impossible to observe this. So why was that? Well, what is 10 to the 16 kilometers? It's pretty big. So it's approximately the size of a small nebula. So we're talking about the neutrino traveling from one star across many stars, much, 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 much larger than you could ever build a detector on Earth to see. So yeah, this is about 1,000 light years. If we're on a little planet down here, we're never going to stop one of these things, no matter how big our detector is or whatever. The only issue with this conclusion was that they did not account for how abundant neutrinos are. But these two physicists did. So Fred Reines and Clyde Cohen had this idea that instead of trying to see a single neutrino, maybe you could just get a lot of neutrinos, and then the probability of any one of them interacting might be high enough where you could see something. So they used this equation here, where they calculated the number of interactions that you would expect. And there are 4 terms here. So the first one is how many neutrinos pass through a given area per second. And the second one is how likely it is for a neutrino to interact. And remember, this from Bethe and Peierls was 10 to the minus 44 centimeters squared. And then T is how long you wait, and N is how big your detector is. So maybe there's some combination of these numbers that could give you a number of interactions is equal to 1. Could you balance all of these different things to figure out how many interactions, or to get a non-zero number of interactions? So in physics, we call this a back-of-the-envelope calculation. We just plug in numbers that we think are reasonable, and they're all round numbers. So we don't pay attention to factors of 2, we pay attention to factors of 10. Just big numbers in broad strokes to see what could happen. So if you're designing an experiment to see a neutrino, you don't want to wait years. You want to wait days or hours or something like that. So that sets your time scale. So you can plug in 10 to the 3 seconds. It's about a third of an hour, let's say. Again, just round numbers here. The exact quantity doesn't matter so much. Now you need something for the neutrino to interact with. You need protons. One source of protons is just water. Water is H2O. Two of those H's, those are protons, and then the oxygen also has 8 protons in it, so that's a lot of protons. So in 100 kilograms of water, which is not too much, that's a couple, I don't know, tens of bathtubs worth of water, let's say, 10 to the 27 protons. How do you get that? Basic chemistry, 10 to the 24 water molecules per kilogram of water, 10 protons per water molecule, easy. So you're already at 10 to the 30 or so in terms of the right side of this equation. So if you then take 10 to the minus 44 in here and you subtract 30 from that, you end up with 10 to the 14 neutrinos per square centimeter per second is what you would need to see one interaction in about an hour. So now we've put some numbers on the problem. How hard is it to get 10 to the 14 neutrinos per second per centimeter squared? So both of these physicists were involved in the Manhattan Project, and they made a little plan, which was to put a nuclear explosive on top of a tower and set it off, and then look at the neutrinos that came off of it. So really easy. I mean, you got a lot of nuclear physics happening. It's going to produce a lot of neutrinos. All you have to do is kind of outrun this fireball, which, how hard could that be, right? But anyway, yeah, so you have your nuclear explosive on a tower. There's a fireball coming at you, but we'll make a measurement before everything gets turned to a crisp. So they set up a little plan here where there would be a trigger line, a signal running from this tower. So when you set up the nuclear explosive, it would connect up to a pump, and it would drop a suspended detector because there'd be a lot of the ground would be shaking and stuff, and that's bad for your electronics, right? So you need your detector actually in free fall as the neutrinos are coming towards it. And this all has to be under vacuum because otherwise air resistance and things like that get in the way. And of course, you need to read out your data at the end of all of this. So of course, you need feathers and foam rubber at the bottom of your shaft because otherwise your detector's toast. And you have to get the data out of it still. So it's a pretty simple plan. And if you're thinking, this sounds a little insane, you wouldn't be too far off. What could possibly go wrong with this? So actually, I hate to break it to you, but this did not happen. So it turned out that the US was very invested in making nuclear energy and doing nuclear weapons research, and a lot of commercial reactors were turning on at the same time. So at the last second, this plan was approved by Los Alamos, but at the last second, they decided that they would move their experiment to a nuclear reactor. And why this is a good idea, I'll just briefly explain how these nuclear reactors work, is that you take a neutron and you bombard a heavy nucleus with it, and what that gives you is some lighter nuclei and more neutrons that keep the reaction going. But these lighter nuclei tend to be unstable, and they undergo beta decay, which produces exactly the neutrino signal you want. So this was deemed to be a better solution to the problem of detecting the neutrino than the elaborate Rube Goldberg machine of setting off a nuclear explosive. So the first nuclear reactor was actually here on the University of Chicago campus, Chicago Pile 1. There's a sculpture of it outside the lecture hall. Fermi was the one who led that team. And actually, if you have some time after the lecture, you can walk across the street. There's a 2-minute walk to the site of this, and there's a little sculpture there that you can look at. But anyway, so Fred and Clyde sent their new plan to Fermi, and Fermi signed off on it. Fermi said, "Oh, this sounds great, and in particular, your new method should be much simpler to carry out and have the great advantage that it can be repeated." So yes, very important in physics to have something that can be repeated, and this turned out to be the winning combination. So the plan was instead to move a neutrino detector over to the Savannah River site. So this is just on the border of Georgia and South Carolina. There's a reactor core that's emitting these neutrinos, and you place a detector about 10 meters away. In between here and the reactor core, there's a bunch of earth that acts as a natural shield, so that's very useful. And the estimated flux from this reactor core was 10 to the 13, so just about what they were looking for to get out of, or to see a signal here. Now, one other part of this is that I think Fred and Clyde were kind of hungry when they wrote their paper, because in their paper they talk about their detector as a club sandwich. And I'll explain what this means in a little bit, but I just thought it was funny because they introduced the detector concept as a club sandwich, but then they keep it going. So not only is it a club sandwich, but they use bread as part of the detector layers. And then finally the meat layers are the targets of this. So they have this kind of detector by a nuclear reactor. It's a club sandwich, and I'll show you exactly what that looks like. Okay, so here's a kind of simplified schematic of the detector that they're going to build. So the bread layers, this is scintillator, and there's 3 of these. The scintillator acts as an amplifier. So as a charged particle enters the scintillator, it's going to produce a lot of light. They then put these light sensors on the end of each of these bread layers. And the meat layers, this is the target. So these are the protons. And they did a little trick, which is they didn't just use water. They added some cadmium to it. And cadmium is a nice element because it sucks up neutrons. And as it sucks up the neutrons, it also emits a little bit of light itself. And that's going to be critical. So then you connect all of these light sensors up to your oscilloscope or whatever, and you read out the voltage as something happens. If you have a neutrino entering into the meat layer here, what it's going to do is it's going to produce this positively charged electron and a neutron in the inverse beta decay reaction that we talked about before. This positively charged electron is actually going to annihilate with the regular electrons in the water, and it's going to produce a big flash of light. So you'll get some initial signal here on your scope. And then this neutron, it actually can bump around in the water a little bit. It can interact, scatter without really doing much, but eventually it gets sucked up by a cadmium atom, and then it emits light of its own. So what you should expect from a inverse beta decay reaction in this experiment is 2 peaks in time, separated a little bit. One a little bit smaller than the other, just because of the energies of the light emitted from these particles. But this would be your signature. So if you set up this detector and then you looked at your oscilloscope, you would expect to see a double coincidence, is what they would call it. So if you just saw this and then you waited some time but didn't see this second peak, that would be a background. Or if you just saw some single peak by itself, it's really the combination of these 2 signals that allowed them to definitively say whether or not this was a neutrino interaction versus just some random noise. Okay, so what did they see? Well, they saw a lot of double coincidences. So they put their experiment by the nuclear reactor. They waited for a long time, and what they saw were a lot of these when the reactor was on and not a lot of these when the reactor was off. And this is considered the first detection of the neutrino in 1956. They took the rate that they measured from this experiment and they interpreted it as the probability of interaction. And what they found was that it was 12 plus or minus 7 and 4 times 10 to the minus 4 centimeters squared. So in really good agreement with what Beta had predicted earlier. So they had done it. And they were awarded the Nobel Prize. They sent a memo, a telegram to Pauly, letting him know that they had detected his neutrino. And Pauly sent back this nice word. Thanks for the message. Everything comes to him who knows how to wait, from Pauly. So Pauly lived to see his neutrino detected. One other thing I'll point out about this experiment is that they had a very good scientific method. So they did a lot of cross-checks, and the result, even after they had the data, took about a year to come out with. They varied the amount of cadmium that they introduced in the water. That should change the frequency of the neutron, the rate that they would see. You could vary the amount of shielding to check out if there was any background that they hadn't accounted for that would not be caused by a neutrino, or that a neutrino would, or that something that was not a neutrino would be stopped by. And then finally, add different amounts of water with different proton content. So heavy water is another option for this, and that also affects the rate. And they could see that the neutrino signal was persistent after they changed all of these different things, confirming that it really was this particle that they had expected it to be. So that was the neutrino detector, the first neutrino detection. But pretty soon after that, people started asking about other types of neutrinos. So between the proposal of the neutrino and the detection, there were discoveries of other types of particles. So in particular, in the 1930s, the muon was discovered. This is a particle that acts basically as a heavier electron. And it decays into an electron. And then in the 40s, the pion was discovered, which decays into a muon plus something else. I have an image here from a bubble chamber, which is a way to view particle tracks in a magnetic field. The magnetic field causes the particles to bend, and by looking at the radius of the bends, you can interpret what the mass of each particle is. So you can look at these bends and know that it's separate particles based on how much they curve. So just zooming in a little bit to this diagram, this is one example of how we know that a pion decays. So you have this pi plus over here. It's bending in this magnetic field. At some point, it comes to a stop, and then there's a kink in the spectrum where it just suddenly changes direction. So what's going on here? Well, this, we think, is changing into the pion decaying into a muon. And then because there's a kink, there's probably some other particle that balances this out to conserve momentum. So that other particle is hypothesized to be a neutrino. So we had already known about neutrinos at the time this image was made, but we hadn't detected another type of neutrino. And this would be kind of unique because it would be a neutrino without producing an electron. So Ryans and Cohen had detected this neutrino. When that neutrino interacts, you produce an electron. This is a different type of particle decaying into another type of particle that's not an electron. And it also seems to have some invisible amount of energy that just goes away, that causes this to look unbalanced. So that was the idea. But you can't repeat the Ryans and Cohen experiment to answer this question. So we actually needed a new type of neutrino source to get neutrinos from pions to make this measurement. So I plan to come back to these in a future lecture, but for now, I'll just give a brief introduction to how we build neutrino beams that produce neutrinos from pions. So the idea is pretty simple. You take a high energy proton from a particle accelerator and you smash it into a block of material. Nothing more complicated than that. When you do that, what comes out is just a spray of pions, as it turns out. And these pions, they're going to be going in every direction, so it helps if you can kind of collimate them a little bit. Particles with charge, you can add a magnet that acts as a lens to focus particles with different charges. So when I add this magnet here in this diagram, the positively charged pions start to go in a line, but the negatively charged one gets deflected. That's fine for our purposes. All we want to see is pions going in a straight line that decay into neutrinos so we can study what those neutrinos are. So now the pions decay after a little bit of time, not very long, and they decay into muons and neutrinos, as expected. So now we have a neutrino beam. We've built a device that takes protons, turns them into pions, and then we get neutrinos all going in a certain direction. It helps if we can block the muons, because those are kind of a background. The key property about neutrinos is that you want a lot of them, but you don't want to have other particles that can cause backgrounds. So you can block all those other particles with some piece of material and let the neutrinos just keep going. And now you have a really clean way of producing neutrinos all in a straight line and those neutrinos came explicitly from pions, not from the beta decay process that Ryans and Cohen were looking at. So this is a figure from a paper that actually set out to do this. This is an experiment that took place at Brookhaven National Lab. They had a proton accelerator there, and they identified the target point here as one side of the facility, and then there was a lot of shielding over here to block particles that could have come out of the interaction point. And if you place a detector here, then the only thing that should make it are neutrinos, which aren't blocked by anything. And so this was the idea of the AGS neutrino experiment. We're also going to need another type of detector, though, to do this. And the reason is that this double coincidence method that Ryans and Cohen used is only valid if the neutrino is an electron type. So we need something that can tell between a neutrino that interacts and produces an electron versus interacts and produces a muon. These two detectors need to actually see the particle coming out of the interaction, not just measure the count rate, for example. So something that was developed called the spark chamber, and it works kind of like Rines and Cohen's detector, flipped on its side a little bit. The concept is that you have a scintillator again, so again this material that amplifies light that's produced, and then these photomultiplier tubes on the end. Now, sandwiched in between the scintillator layers is a gas volume and metal plates, and I'll explain why in a minute. So as charged particles pass through the spark chamber detector, what they do is they ionize the gas. They remove electrons from the gas and cause these ions to just kind of sit around. But they also produce a flash of light as they travel through the scintillator, just like in the Rines-Cohen experiment. Charged particles passing through the scintillator causes a flash of light. And what you can do is you can do timing with this. So when the charged particle comes through, the ions are sitting there. The PMTs see light up here, and you can use that to trigger the turn on of a high voltage signal. What that looks like is shown in this video over here. So the charged particle passes through, you have this trail of ions sitting through, and when you put the high voltage on it, it causes sparks. And now you can see something in your detector based on, or whenever a charged particle comes through. So this video is just showing some of those tracks that would form on these ion trails as charged particles came through. And why this is important is because muons and electrons do different things in spark chambers. So on the left here, I have the muon, which we saw before on the previous pages. That particle is going to leave a trail of light when it triggers the detector. It's also a heavy particle, so it's not easily deflected. But electrons, on the other hand, those are pretty light. So as the electron passes through, it creates sparks in kind of a random pattern here. And by looking at the different distribution of the two types of spark chamber events that you can tell whether or not the particle that passed through was an electron or a muon. So that's the basic idea. So now we have a new neutrino source and a new type of detector. Let's see what we find. So these are images from this paper here where they did this experiment. This is a spark chamber at the end of a neutrino beam, and on the left I have some examples of tracks from that experiment, and on the right I have some examples of what they called showers. So remember, the tracks are what we think are induced by the muon neutrinos, and the showers are what we think are induced by electrons passing through the detector. So you can see really clearly that these tracks are a lot less noisy than these shower events. So basically what we were saying is that electrons coming through will scatter around a lot, produce a lot more light. Now, the physicists who did this experiment, they counted all of these up when they had the neutrino beam running, and what they found was that they found way more track-like events than shower-like events. So in particular, they found 34 of these track-like events and only 6 of these shower-like events. And if the neutrino that came out of the pion decay were really an electron neutrino, then it would produce electrons when it interacted, just like in the inverse beta decay process. But since it didn't, it produced these track events, we actually can conclude that it's a really fundamentally different type of particle. So this was awarded another Nobel Prize. The 3 physicists were Leon Lederman, Melvin Schwartz, and Jack Steinberger. And the conclusion was that the muons from these pion decays produce muons, not electrons. And the Nobel Prize here reads, for the neutrino beam method and the demonstration of the doublet structure of leptons through the discovery of the muon neutrino. Pretty wordy, but we'll get to that throughout this lecture series. So here's a picture of Melvin Schwartz with the spark chamber kind of to scale, showing some of these track-like events that led to this discovery. So at this point, I'm just going to mention a little bit about what we know so far and summarize a little bit. So in 1930, we had Pauli's beta decay, where you had a nucleus and it becomes another nucleus, and there was an electron emitted and there was another particle emitted. Just a hunch. 1933, Fermi comes along and does the math. Really figures out that it's a neutron turning into a proton, producing an electron plus a neutrino. It then took about 23 years before Rines and Cohen came along and actually found the proof of this neutrino's existence. And then 1962, Letterman et al. Discovered the second type of neutrino. So we can summarize all of these things that are happening with some diagrams. On the top here, what I'm showing is that the pattern seems to be that you have a neutrino coming in, interacting with either a proton or a neutron, and then either the electron or the muon coming out, and then changing the proton into a neutron. So this is the basic pattern that we see. So in inverse beta decay, it was the electron neutrino, so the new E, interacting with the proton, producing the neutron, the N here, and then the E. But for Letterman and Schwartz and Steinberger, they had the mu version of this coming in and producing a muon version. In their experiment, we couldn't tell the difference between the protons and the neutrons in the before or after the reaction. But what you can then start to do is see how this theory fits together in a bigger picture. So just taking this simple diagram here and rearranging the pieces, you now get the beta decay that we saw earlier. A neutron decays into the same three pieces that are in this diagram, just like this. So to end this first lecture, I'm going to talk about a little bit the big picture of particle physics, just give you a little preview of what's to come. So this is a picture of the standard model, and I plan to revisit this in future lectures. But it describes all of the fundamental particles we know about and the forces that govern their interactions. So you can look at particles that have electric charge, and we say that those are, they interact via the electromagnetic force, via the photon, which you might have heard about. It's just another word for light. So these are all the particles that have electric charge. You can see here. There's also the particles that interact with what we call color charge, and their force carrier is known as the gluon. And this is also known as the strong interaction. And this is what we know binds together protons and neutrons now. So I haven't really talked about this, but it will come up in the future. And then finally, the particles that experience the weak force include all of the quarks, the electron muon, and this tau particle, which I'll talk about in the next lecture, but also these neutrinos. And it's by understanding the different ways that these forces can go together with different particles that we can start to describe particle interactions more rigorously. So in particular, I'll focus in a little bit on the weak force, which what we saw for the neutrinos. And the weak force interacts on pairs of these particles from this table. So you can pair up the up quark up here, this U, and the down quark down here. And you can pair up this E and the new E here, this electron neutrino and the electron, the muon neutrino and the muon, like this. And the weak force interacts on pairs of these things. So focusing on these again, with this force carrier here for the weak force, which we call W, we can start to put these together into different diagrams. So that pair from before, from that last page, is the electron neutrino and the electron. That pair from the quarks was the up quark and the down quark. And what the weak force is doing is it's swapping the particles in these different pairs. So swapping the electron neutrino for the electron, swapping the up quark for the down quark. We call this the charge current interaction. And we can understand what's happening in beta decay or in inverse beta decay by then grouping up the quarks into the nucleons that make up the nucleus. So a proton is composed of an up quark and two down quarks. A neutron is down quark, two down quarks and an up quark. And what you can see is that through the weak interaction, you change a proton into a neutron by swapping one of the quarks in this interaction. And then you can also extend it for pion decay. So here's a diagram for pion decay. Up quark switches to a down quark. I'll explain what this bar means a little bit later. And then also the pair of the muon neutrino and the muon. So this is our model of particle physics today. So to summarize, today we saw a really nice story. We had a problem. We started with this beta decay spectrum that we couldn't explain. A new theory was developed that predicted a new particle, which was then motivated some new technology that allowed us to detect that particle. And then the particle was confirmed, and it fits into our big picture of particle physics. So that's great. Is there anything left to do? Well, maybe. So actually there was a pretty smart guy named John Bacall who had one burning question for his entire life, which was, do we know how the sun shines? And John Bacall was very clever because he actually saw in neutrino physics an opportunity to understand the neutrino, or to use the neutrino for an application. And the reason is because fusion in the sun is happening all the time, and what Bacall realized is that as fusion is happening, you get a lot of neutrinos produced. So this picture is showing two protons fusing together, making this H2 atom here, and then producing a positron and an electron neutrino. And so what Bacall wanted to do was to measure the rate of neutrinos from the sun and use that to infer something about solar neutrino, or about solar physics. So a great application. Can we understand what's happening in the sun by looking at the neutrinos produced from fusion in the sun? The only problem with that is that we'll need a new type of detector, which I'll talk about next week. So with that, thank you so much for your attention.